Touch a small magnet to an iron nail, and the nail jumps upward, but a wooden splinter and an aluminum tab stay put. The difference is not that iron contains magnetism, while the other materials contain none at all. Every material responds to a magnetic field, but the type and strength of that response depend on its electrons and atomic structure. Electrons carry magnetic moments associated with quantum spin and orbital motion, although spin is not literal mechanical rotation. In iron, a quantum interaction called exchange coupling encourages neighboring magnetic moments to point in the same direction. Large groups of aligned moments form magnetic domains, each behaving like a tiny region of strong magnetization. An unmagnetized iron nail contains many domains pointing different ways, so their external fields mostly cancel. Bring a magnet close, and favorable domains grow or rotate until the nail develops a strong induced magnetic pole near the magnet. Because the magnetic field is stronger near the magnet than farther away, that induced magnetization produces a net attractive force. Soft iron can lose much of this alignment after the magnet leaves, while some steels retain it and become permanent magnets. Wood is different because most of its electron magnetic moments cancel in pairs, and it has no ferromagnetic domain structure. A magnetic field induces only a minute opposing response in ordinary wood, a behavior broadly called diamagnetism. Aluminum has unpaired electronic moments and is paramagnetic, so a static field tends to align them weakly with the field. That alignment is millions of times less cooperative than iron's domain response, so a refrigerator magnet cannot visibly lift an aluminum can. With a sufficiently strong field and a steep gradient, aluminum can be attracted, but the force is small under everyday conditions. Move a strong magnet rapidly past aluminum, however, and a much more obvious effect appears. The changing magnetic flux drives circulating eddy currents in the metal, and those currents create their own opposing magnetic field. According to Lenz's law, the interaction resists the change, producing magnetic drag or even brief repulsion without making aluminum ferromagnetic. That is why a magnet can fall slowly through a thick aluminum tube, even though it will not stick to the tube wall. Temperature also matters. Above its Curie temperature, a ferromagnet loses the ordered state that gives it strong, spontaneous magnetization. Material labels can be misleading, too, because some stainless steels are magnetic and others are not, depending on crystal structure and composition. Iron, cobalt, nickel, and many engineered alloys respond strongly because their atomic moments cooperate across domains. Wood and aluminum still interact with magnetic fields, but their ordinary static responses are too weak to win against gravity and friction. So the nail leaps, not because magnetism ignores everything else, but because iron amplifies the field through collective quantum alignment.